Hi, my name is Gerardo Figueroa and I am a biomedical engineering major.
My name is Hannah Johnson. I'm a biomedical engineering major.
My name is Mohammed Al-Bouri and I'm an industrial engineer.
My name is Brian Zhang. I'm a biomedical engineering major.
I'm Carmela Compuesto and I'm a biomedical engineering major.
Hi, I'm Kendall Starring and I'm a mechanical engineering major. We are team 21045 and we created an automated media exchange system for a dynamic tissue engineering bioreactor for Dr. David Margolis.
In 2019, a senior design team built a bioreactor that would replicate the mechanical forces that cartilage tissue in the body experiences onto engineered tissue. The bioreactor includes two motors, a vertical compression force motor and a horizontal shear force motor, that replicate the mechanical loads applied during normal gait activity on cartilage tissue scaffolds. One of the critical components of tissue engineering is feeding the tissue with growth medium, which is a liquid containing essential nutrients for cell growth. This medium must be changed regularly in order to keep the cell supplied with fresh nutrients. A unique requirement of tissue engineering and cell culture is the need for sterility, and although current practice attempts to meet this requirement, contamination is an ongoing obstacle to successful tissue engineering experiments. The previous bioreactor required users to remove the cartilage tissue from the sterile system every time the medium is exchanged, which presented the opportunity for contamination to be introduced.
This project aimed to modify the existing bioreactor to create a comprehensive tissue engineering system that would prevent contamination. The Automated Media Exchange System, or AMES, for the dynamic tissue engineering bioreactor automatically removes old medium from cell wells and replaces with new medium, allowing the well plate to remain within the sterile bioreactor environment for the duration of the experiment. Furthermore, the AMES incorporates a contamination detection system, alerting users to possible tissue contamination that would compromise the integrity of the system and allowing them to quickly take action. This system is designed with an easy-to-use software interface and consists of easily reproducible and cost-efficient components that are sterilizable and durable.
Our system must automatically exchange the cell growth medium. It must measure the pH of the medium. It must maintain a sterile environment, and it must interface with the existing system.
In designing our system, we aim to meet all of our system requirements and to create a low-cost system that would be easily reproducible should any of the components need replacing. Therefore, the majority of our custom system components are 3D printed. Furthermore, the system is easily disassembled for sterilization and fits within the incubator environment. Our original design concept included a moving feeder system. The moving unit would incorporate both injection and extraction systems, as well as the photoresistors used for pH monitoring. However, this design concept was changed as we learned that it is very difficult to reapply the conditioning load to the scaffolds once the original load was released because the scaffolds could shift. Therefore, we chose to pursue a new design that does not require the load to be removed.
Our new design concept incorporates medium injection into the bowl, supplying the loads to the scaffolds. Extraction is performed through a well plate cover that also houses the photoresistor used for pH monitoring. This design concept was selected in order to minimize the number of tubes and wires that are feeding directly into the tissue well. The existing bioreactor incorporates strain gauge with many wires entering each well, and the extraction tubing must enter each well directly in order to remove as much old medium as possible. By injecting new medium through the force applicator bolts, we are able to elevate the injection tubing and reduce the clutter entering the wells.
In designing our system, we extensively researched requirements for media exchange and cell culture. We modeled our fill rate requirement off of an established fill rate for a small well plate size and scaled this rate for the larger volumes of the well plates our system caters to. We chose this lower of the two rates to avoid damaging the growing tissue. The fill rate allowed us to analyze the time required to fill the wells. Growing tissue should not be left without medium for more than 2 minutes, and we found that our chosen flow rate of 0.6 milliliters per second allowed the system to complete the exchange process in less than 1 minute, even when dispensing the maximum volume. We also analyzed the power required by our system to ensure that it could operate on the standard power available in the lab. We found our system to be well under this requirement.
To mitigate the challenges of integrating our design with the existing system, our team prototyped as many of the components as possible. We created 3D printed versions of all custom components that required manufacturing and used these prototype components to perform testing to ensure all specifications and requirements were met. Using prototype components allowed us to perform initial testing to ensure that our system would work and perform as expected. After all of our custom components were tested, final versions could then be manufactured and integration assembly could be completed.
One of the most important requirements for our system was that it be easily operable via a graphical user interface, or GUI, as seen in this video. The user can select which wells are being used, as some experiments may not use all wells. They may then select the volume of medium to be dispensed. For the 6-well plate, each well can hold a maximum of 17 milliliters. The user can then initiate the exchange process, and the GUI informs the user that the media exchange process is being executed. The final function of the GUI is the pH monitor. The user can select to check pH, and the system will display the calculated pH for each well. Additionally, if one of these pH values is detected to be indicative of contamination, the GUI informs the user through an alert.
The performance requirements for our system were verified through testing in the lab. Many of our requirements were verified through demonstration, such as the integration of the system within the existing system, the ease of operation, and the automatic exchange of medium. In order to verify that our system is sterilizable and can maintain a sterile environment, we sterilized the system after it had been exposed to contamination, then swabbed it and verified that no contamination was present after 2 weeks. To verify that we met timing and fill rate requirements, we repeatedly ran the injection program and measured the length of time required to move a specified volume of medium.
We concluded that the automated media exchange system was able to automatically change media from both the 12 and 6-well plates without introducing contamination into the samples. Additionally, the design of our user interface allowed for easy understanding of its operation and control. By observing that an untrained user can easily operate and understand the system, we're confident that a long training session will not be needed. Furthermore, the user will be able to observe the condition of each well plate and receive an alert if there is any contamination in the samples.
Through this project, we learned the importance of fully understanding the existing system as well as the project goals before beginning the design process. Because we had never seen the existing system in action, our initial design concept was not the best option for interfacing with the current system, and we had to redesign in order to facilitate easier operation by the user.
In addition to the typical challenges faced in an engineering design project, our team faced further challenges due to the current COVID-19 pandemic. The biggest impacts the pandemic had were prolonged manufacturing time and, more importantly, limited access to the lab. The limited lab access due to campus restrictions delayed our team from viewing the existing system, which made it more challenging to implement our team's modifications and delayed prototyping until the second semester. Due to this, we did not have a good sense of how the existing system operated, and much of our team's preliminary work was done using only previous documentation provided by the project before, and many of our modifications also needed to be redesigned. Our prototype parts also took much longer to manufacture than expected, which greatly delayed our assembly progress, testing timelines, and troubleshooting process.
We would like to thank our sponsor, Dr. David Margolis and the Orthopedic Research Lab, for their assistance with this project. We would also like to thank the Biomedical Engineering Department for supporting the project, and our mentor, Don McDonald, for his guidance throughout this process.